Hello, welcome to the channel of Nandagiri Academy. Here, this is the next video in the series of multiple integration, and now we shall move over to triple integration. So, now as double integration is for the um, uh, function over regions, two-dimensional regions. We do triple integration for the functions that are defined over three-dimensional solids. So what it geometrically means is something that we shall not discuss. Basically, in case of a function of one variable, the integration uh, it has a geometrical interpretation that it is the area under the curve of the area under the graph of the function. In case of a real valued function of two variables, it is the volume that is captured between the graph of the function and the region between which region over which it is defined. And in case of triple integration, uh, that idea extends to the volume of the four-dimensional, you can say four-dimensional entity that is defined over the three-dimensional solid, which we cannot visualize, and therefore we shall not rather bother ourselves about interpreting it geometrically. What we shall see is um, actually integrating functions, real valued functions over um, uh, three-dimensional solids. That means triple integration. How to integrate, how to determine the limits of the integration if a solid is given, and also how to use it for finding out the volume of a solid. Now, in the previous lecture, we have seen how double integration can be used to find out the area of a region. Now, similarly, triple integration can be used to find out volume of solids, and very soon we shall see how to do all of these things. So, first, triple integration. So, let us recall how we the general form of um, double integration. We always integrate a function of a real valued function. We are, of course, we are concerned with real valued functions, and we typically do iterated integrals. So f of xy, let's say dy dx, this is the iterated integral, and in this case first we integrate with respect to y, and y is generally a function, the limits of y are generally functions in x, g1 and g2, and then we integrate with respect to x, and then x typically is the function over x. So after integrating with respect to y and substituting these limits of integration in terms of x, we get a function in x alone, and after integrating that we get a function in x, and then we substitute these limits x, a and b, and we get a real number. That is how we do the double integration, the general form of definite double integration. Now in case of triple integration, this now here we are integrating with respect to two variables. Now we are going one step ahead, and we have three variables, and so therefore we have triple integration. So we shall have a real valued function of three variables, dz, dy, dx. This order can change, okay, depending on the situation. Now here y was a function of the limits of y were functions of x. Now here the limits of z will be functions in x and y both. Generally, in general, g1 x comma y, g2 in x comma y. The limits of y will be function in x alone, h1x, h2x, and the limits of x will be constants a and b. See, after we integrate f with respect to z, and then when we substitute these function values in the integral that we obtain g1 and g2, we get a function in g1, we get a function in x and y. Then we integrate it with respect to y, and then we substitute the limits, and which are in terms of x alone, and then we get a function in x alone. Then we integrate it with respect to x, which gives us function in x, and after substituting the limits a and b, we get a real number. So that is how we typically compute the integral. Let us take one example. Integral, let's say compute triple integral x dz dy dx. Z varies from 0 to xy. Observe here that g1, here the function g1 is uniformly 0, whereas g2 is a function in x and y, which is xy over here. Xy is a function in two variables x and y. Then the limits of y are 1 over x. So this is these are functions in x alone, and the values between which x varies are 1 over 3 and 3. So let us go ahead and compute it. Let me call it I. So I is equal to, so our method for finding out integral will not change. X is constant with respect to z, so therefore this integral will become now substituting xy for z. Now here z was the variable, so we shall be substituting these limits for z in here. So that will give us x square y dy dx. Now look here, this we have now this has now reduced to double integral after solving after integrating with respect to z. So now we are in our familiar domain of two integration and of two double integration. So now we shall proceed as we used to do earlier. Now we are integrating with respect to y, so x square is constant and integral of y is y square over 2. So what we get is x square y square over 2, and the limits of integration are 1 over x and x. So nothing very exciting now here after this. We can take this 1 over 2 outside this, and what we have inside is, after substituting for y, it is x power 4, and here it is 1 over x the square, which cancels out with x square and gives us minus 1. Here we must have dx. So we have 1 over 2, and now the integral of this with respect to x is x power 5 over 5 minus x 1 over 3 3, and now whatever this number is, we can compute that. We can complete the computation, but the whole point of this was to show you how to compute the triple integral. So the process of integrating is not much different from that of double integral. What is somewhat challenging in case of triple integration is, suppose the integral is given, then computing the integral is not very difficult. But if the region or rather three-dimensional solid is given over which we want to integrate, then finding out the limits of integration can be somewhat challenging in case of 3 dimensions. Let us take one example. Compute. Triple integral of y dx dy dz. I would rather change the order just for the sake of you can change this order, okay, that's not a problem. Over this solid S, where S is the tetrahedron 12x plus 20y plus 15z equal to 300 lying in the first octant. So now, as we have quadrants in plane, we have octants in 3 dimensions. So in the first octant means the part of the space where all x, y and z coordinates are non-zero. Alright, so now here first we have to draw that solid, and once we draw the solid we have to decide in that solid what are the values between which x, y and z vary, so that we can set the limits for each of the variables and then compute the integral. Okay, so now let me draw here the octant. This is x axis. Now it is up to you how to represent axis. Sometimes this is typically taken as a horizontal axis, is typically taken as x axis. Some people choose to take this as y and this as z. Some people choose to take this as y and this as z. So you can exercise your choice. I am taking this as z at present. There is nothing special about this choice. Alright, so how are we going to draw this tetrahedron? So tetrahedron is some sort of a prism, which prism generally has equal sides, but tetrahedron may not have equal sides. So fine. So what is this tetrahedron? So how are we going to draw this? Now if we set y and z both equal to 0, then we get a point that lies on the x-axis and that lies on the tetrahedron on the x-axis. So substituting y and z equal to 0, we get the equation 12x equal to 300, which means x equal to 25. So x equal to 25 is a point on tetrahedron and is a point on the x-axis that lies on the tetrahedron. Similarly, let us substitute x and y equal to 0. That gives us equation 15z equal to 300. That means 20z equal to 20, and after substituting x and z equal to 0, we get 20y equal to 300, which means y equal to 15. So this is y equal to, let's say, 15. So these are the 3 points that are lying on the coordinate axis, that are lying on this tetrahedron, and by connecting these 3 points we shall get our tetrahedron. Look at this. This is a 3-dimensional diagram. This part, which is bound between x, y and z in the positive, these are the positive coordinates, and this region, or rather this solid, is the required tetrahedron, and we want to integrate this function y. So the integrand, that is the function that we want to integrate, is not very complicated. It is just y. So that the difficulty is not in the integrand. The difficulty probably, if at all, lies in determining um, the limits of integration. All right, so what we shall do is we shall let x vary freely. So now this is 25, as we saw, x is 25, this is 50. So we shall let x vary from 0 to 25. Accordingly we shall see how z varies, and when x and when we have determined how x and z vary, we shall accordingly set the limits for y. All right, so now note that this is the line that lies in the xz plane. Now in the xz plane y is 0, so this line is 12x plus 15z equal to 300. So can we reduce it? I think yes, we can divide the whole line, the whole equation by 3. That gives us 4x plus 5y equal to 10. Four x plus 5z equal to 10. So maybe we can keep it as it is. Maybe it is unnecessary, because afterwards, okay, 15z equal to 300. All right, fine, okay. So for every x here, so for every x here, what is the z here? Okay, suppose if you take this as x is varying from 0 to 25. For x, z is going from 0, here z is 0, it will move from 0 to this point. So this point lies on this line. Okay, so the z coordinate of this point can be computed by solving this equation. So z equal to 300 minus 12x divided by 50. So for every x, so now we are setting setting limits for each of these variables. X is varying from 0 to 25 without any restrictions, and for every x, z is varying from 0 to 300 minus 12x. We shall simplify this afterwards, but for the time being, let us keep it as it is. We can write, after dividing both numerator and denominator by 3, we can write this as 10 minus 4x divided by 5. Okay, so this is alternative expression for this. Now what is y? The most crucial thing out of all these. See, we want to cover this whole tetrahedron. Alright, so we must take into account every point that lies inside this tetrahedron in order to cover the whole solid. In order to integrate over the whole solid, we want to take into account every point in this tetrahedron. Now consider this sort of a triangle which is parallel to this triangle lying in the YZ plane. Also consider this triangle that is lying in this parallel to this triangle in the largest triangle in the YZ plane. Also this triangle. Also this triangle. Now do you see that the whole prism can be thought of as made up of these sliced these triangles or other slices which are of the triangular shapes in this fashion. And if we can rather add up all or rather combine all these triangles, then we get the whole tetrahedron. So that's what we shall try to do. So in order to cover the whole prism, we shall cover all such triangles. Now we have seen that for every x over here, x moves from 0 to 25. For every x in this fashion, z moves from 0 to this quantity. Alright, 0 to this quantity. And what is the y? Now y is varying in this direction. What is y? That it is, how is y varying? Suppose we can find out the limits of y, rather range between which y is varying in this triangle, then we are done. Okay, then we can, then at least for this triangle we know the limits between which y is varying, and in this fashion varying over all such triangles, we shall get the whole prism. Now here in this case, for this x and for some z in between, y starts varying from 0 because on this segment y is 0 because this point lies in the xz plane, and in xz plane y is 0. So 0, the y will start varying from 0, and up to what will it continue to vary? It will continue to vary. It's just arithmetically it's very easy. Just solve for y using this equation. It will be 300 minus 15z minus 12x over 20. So for this point, the maximum value that y can take is this. As soon as y takes value greater than that, it will go beyond this, because value of y is restricted by this equation. Alright, so therefore for every such x and every z that satisfies this inequality, y must vary from 0 to this. So you can also cross check. For example, when z and x are both 0, that means here when z and x are both 0, y is varying from 0 to 15, which is 300 over 20. Okay, so by taking various values you can check. For example, here at this point, um, x is 25, so you can see that there is no scope for y to vary, so y should vary from 0 to 0. That means, as you can see over here, if you multiply, if you substitute x equal to 25 over here, 300 minus 12 multiplied by 25 is 0, and since z is also equal to 0 over here, you can, here it becomes, this right hand side becomes 0, so therefore this seems to be okay. So practically what we have done is just algebraically we have just solved for y using this equation, but you can check that intuitively this is correct. So now we have set the boundaries, or rather we have set the limits for each of these variables. So now what remains is to actually compute this integral. Let us try to do that. So we shall use iterated integral y dy dz sorry dx. Y is varying from 0 to whatever it was, 300 minus 15z, I guess 15z minus 12x divided by 20. See that y is a function in x and z. Every variable with which we are integrating is a function, rather the limit of that is limits of that are functions in the remaining two variables in the first case. Okay, now z is varying from 0 to we can take this simpler expression now, 10 minus 4x. Here we can write this one, but you can write 10 minus 4x over 5, 10 minus 4x over 5, and x is varying from 0 to 25. Let us compute that. I guess we should not write this, because we can straight away. So the integral of y with respect to y is dy square over 2. this is 0 to 25. So it is I'm sorry, this should be written as dz dx 300 minus 15z minus 12x the square. We can take this 2 outside, 1 over 2. dz dx. Now here I think change of variables, change of the order of integration can work well. So when we are integrating y, we better keep it at the end, so that it is an exercise. You can take it as an exercise to, and instead of as we have taken this order of integration as dy dz dx, you can rather integrate it like dx dz dy. That could be the best way to compute the integral, but then in that case we shall have to change the this limits of integration. Alright. Okay, so here we can here now that we are integrating with respect to z, 300 minus 12x can be considered as a constant, so we can write this as alright, maybe 10 minus 4x over 5. So 300 minus 12x the square plus 15z the square, so 225 z square my negative minus 30 z multiplied by 300 minus 12x. This whole dz dx. So this is constant with respect to z, so it will be 300 minus 12x square z plus 225 z cube over 3. It is the integral of this minus 30 z square 300 minus 12x divided by 2. And now this is the integral of this with respect to z, and then we have to substitute the these limits. So we can just write it here as zero to 10 minus 4x over 5. Please pardon me for this handwriting. Now if we substitute for z, when we substitute 0, the whole expression will become 0, because everywhere z is present. So we only have to worry about this part. So 300 minus 12x is okay. So 300 minus 12x can be written as after factoring out maybe 3. So 3 square is 9. It is 10 minus 4x the square multiplied by z, which is 10 minus 4x over 5. So it is cube over 5 minus this 3 divides 2 to 5, so that is 75 z power 4 over 5. I'm sorry, we have to substitute, right, for z cube. So we have here 10 minus 4x over cube over 125 minus 15 z square, so that is 10 minus 4x, 10 minus 4x the square multiplied by 4, so that can be written as cube, and this 50 multiplied by 4 can be written as 60. And this square of this 5 in the denominator becomes 25. So fine. So this is something that we shall have to integrate with respect to x. Okay, so fine. So possibly not the best way to do it, but the purpose of this example was to show how to set the limits of the integration in case of the solid when we are doing triple integration. The Probably changing the order of the integration can work better, and here something might have, I don't know, I'm not very good at computations, so something might have gone probably wrong, but let's see what is happening over here. If we sort of equalize the denominator, what we get is, here we might have to write this as 25 multiplied by 9. um, so 25 multiplied by 9 is 225 minus 75 minus maybe um, 300 divided by 125, 10 minus 4x the cube dx r. Alright, so that is 375, 225 minus 375 is negative of 125. Okay, wait. Minus negative of 375, 225, so negative 150 divided by 125, 10 minus 4x the cube dx. Probably we could have factored out 2 from this 10 minus 4x even earlier. Let's go up and see what is happening. Here okay, so fine, so I will just leave it to you to further solve it, and also just check whether use this same idea of changing of covering the whole solid using rather by dividing, rather slicing it into smaller triangles, and check whether changing the order of the integration works better. That means what we did here was we integrated y with respect to y first, which probably gave a little bit of trouble to us, because that introduced a square term, and then we had to deal with all square terms afterward. But suppose that here we had x in this place, then y would have become a constant. You could have simply pushed it outside, and probably things would have become simpler. But in order for that to happen, we must change these limits of integration as well. So please try doing it. Since we are integrating y, keep y at the end, integrate with respect to y only in the end. Try to integrate with respect to x and z first, but accordingly adjust the limits of integration, and then try to get the answer, and also try to finish this problem yourself. Just check that answer that you get by in this way, and then answer by changing the order, both match. Okay, I might have made some mistake in this, okay, probably, but just you point out the error and finish the problem. But I hope that, see, please don't get carried away by what, by the actual computation. The objective was not to actually compute this integral. It was to show you how to uh, set up the um, limits of integration in case of this tetrahedron. But these shapes may vary, and accordingly you have to think and decide the limits between which all these variables, the ranges of these variables. All right, so fine. So now, the next and probably the last thing, before we learn to um, change we learn to change variables in triple integration. It is the computing volume of solids using triple integration. So as we saw in case of double integration, if we integrate over a region by setting this function equal to 1, that means if we have a region R, and if we integrate the function f, we set f of xy equal to 1, and if we integrate, then we get the area of R. Similarly, if in case of triple integration we have a solid S, we set function f of x comma y comma z equal to 1, and if we integrate this uniformly constant function 1 over S, we call, when in case of double integration we use dA as the differential. Here in case of triple integration we use dV. So this gives us the volume of the solid. Alright, so we shall not in that case I explained, I have given explanation. You can recall it and try to relate these two things together. I will not explain this again, but for the time you can just remember that if you want to find out the volume of a solid, you can simply integrate over that solid by setting function to be equal to 1. Alright, so now suppose, let's say this tetrahedron, if we wanted to find out its volume, what could we have done? We could have simply set this function. Here we have been given the function to be equal to y. We are integrating y with respect to y, z and x. If we set this, if we change this y to 1, then we shall get the volume of this tetrahedron. So let us try to compute the volume of this tetrahedron. What we suppose, what were the limits of integration? These were the limits of integration, and now our function is uniformly equal to 1. So 1 multiplied by dy, dz, dx. Remember that y is varying from 0 to this, so do not mix up the limits of integration. Now this becomes integral of dy is y, so 0 to 25, 0 to 10 minus 4x over 5. So it is y 300 minus 15z minus 12x over 20 dz dx 0 to 25 0 10 minus 4x divided by 5, and now we have here 300 minus 15x minus 15z minus 12x over 20 dz dx 0 to 25 so x is constant with respect to z, so what we can do is 300 minus 12x divided by 20 minus 15z over 20, which is 3 over 4 3z over 4 dz dx 10 minus 4x over 5, okay, is equal to 0 to 25 alright. This is 0 to 10 minus 4x over 5. Now here it will be, this is a constant with respect to z, so 300 minus 12x over 20 z minus 3z square over 4 multiplied by 2, so 3z square over 8. This can be now changed with, we can rather zero 10 minus 4x over 5 dx 0 to 25. Alright, so now here we can take out we can factor out 3, so 3 over 20 and then what remains inside is 10 minus 4x, and then z is 10 minus 4x over 5. So is 10 minus 4x the square over 5 minus 3 z square. So 10 minus 4x the square divided by 5 square, so 25 minus 10 minus 4x the square divided by 25 multiplied by 8, so that is 200, and this whole is to be integrated with respect to x. What is this? This quantity is double of this, because this is 3 times the same. The numerator is the same, whereas denominator is half. So what we get is 0 to 25. It gives us 3 over 200 10 minus 4x this square dx. So 0 to 25, we can factor out 2 over here, so that gives us 4 3 over 50 5 minus 2x and the square dx. Alright, so again now here I will leave the rest of it for you to solve. It is now very easy to do. You can directly use the formula, or you can also probably expand this, and then you can substitute and then solve it. So that will give you the volume of that tetrahedron. Also, if you when you find out the volume of the tetrahedron, also check whether the volume of the tetrahedron is correct or not by using the ready formula for tetrahedron. You may get the formula for tetrahedron on the internet. Check what is the formula for tetrahedron. It can be given in terms of the base of the tetrahedron and the perpendicular that will drop from the vertex onto the base. So that will give you the volume, and check whether the two values match. Alright, so that is all about the triple integration. So we have covered the first part of triple integration. In the next lecture we shall see how to change the formula for the change of variables in case of triple integration. Alright, fine. See you in the next lecture. Bye.